Okay, let's now go back to the Tower of Hanoi problem there. So I would like to go over with you briefly the Java code. I think it's quite a nice case study. It's a difficult one, but I think it's manageable. I would like to go back to iPad first, just to talk about our general strategy very quickly. And then you will see that the correspondence between the general strategy conceptually is very close to the actual Java code. I'll show you, okay? Let's review what the problem is very quickly, and then we'll go from there. So we're solving Tower of Hanoi. Let's say we got a problem where we got 3 disks. Let's say we got A on the top, B in the middle, and C at the bottom. So it's sorted in the ascending order. And then we got 3 packs. We got pack number 1, we got pack number 1, pack number 2, and pack number 3, okay? Now, what's the problem? The problem is we want to move this tower over here of size 3, A, B, and C, from pack number 1 to pack number 3. So what this really says implicitly is we're going to use pack 2 as the intermediate pack for us to help, right? So that's something very important. Let me repeat it again. The problem is we want to move A, B, and C, the entire tower of size 3, from pack number 1 to pack number 3. And you should realize whatever pack that's not mentioned here is the intermediate one, okay, intermediate. Okay, let's see what the strategy is. Again, if you want to solve the problem recursively, you should really divide the problem into subproblems that is strictly smaller. In this case, the way we divide is, let's say we have a smaller tower which contains just A and B. This is a valid tower because A is smaller than B. It's simply a tower of size 2 rather than 3. So this is the strategy. We're going to say conceptually, we're going to move A and B from pack number 1 to pack number 2. As I said before, the eventual goal is to move from P1 to P3. So P2 is the intermediate one we can make use of. Okay? So now, once we move, so that's stage number 1. Move A and B from P1 to P2. And then step number 2, we want to move C over here just by itself from P1 to P3. And then we got C over here. Okay? So that's the second step. So C is gone. You can see P1 is now empty. And then step number 3, we want to move AB, this tower over here, again from P2 to P3 because eventually everything has to be on P3. So after this, AB is going to be on stack of ABC, right? So that's the kind of the process. Let me go a little bit more details into it. What do I really mean when I say move AB from P1 to P2? This is just another problem which I cannot solve immediately. So what I need to do is I got to do recursion on that as well. But now how do I divide this problem here into smaller problems? Just like how I did before. So now I got one tower of size 2, A and B. What I can do is I can say now, let's say I'm going to treat a tower of size 1 as a subproblem there, like the one I highlight in green. And then I can divide the original tower into 2 parts. One part is everything else except for the bottom one. And the second part is the bottom one. In this case, just B. Okay, let me just highlight that. So it's B here. Okay, 2 parts. So now let me just divide this a little bit further to see what we can do. Okay, now just this first stage here. How do I now solve this problem over here? So now the problem is, let me just use a different color here. So now that means I want to move AB, let me just draw A and B over here from P1 to P2. So this means P3 at the moment is going to be the intermediate pack I want to use, right? So now I want to move AB from P1 to P2. So now what should I do? I want to divide this problem over here into, first of all, I have this tower that is strictly smaller and also the bottom one, just like what I did before. Okay. Now how do I do? Let me just highlight again. So it's going to be from P1 to P2. And P3 is going to be the intermediate one. Okay. Now let's just write it down just to get you more understood. So now how do I do? The first stage, we should really move the top tower there. So now let's say move A over here, just a tower just by itself. A from, now in this case, give me some help. From where to where? P1 to P3, right? In this case, because P2 is the ultimate goal, so P3 will be the intermediate. Thank you. P1 to P3. Now, second stage, Once A is gone, A will be moved. So let me just get rid of this. A will be actually over here, P1 to P3. Now, what happens to the second stage? What should I do? Move which one? B, right? Because B is left over here. So now move B from, now in this case, from where to where? P1 to P2, exactly. Very good, thank you. P1 to P2. You can see that this subproblem here, the only thing that's different, there are two things that are different. First of all, the tower we are trying to move is different, A and B, rather than A, B, and C. And also, we are moving from P1 to P2 as opposed to from P1 to P3, okay? And then finally, now we know that, so after this, we're gonna have B will be moved from P1 to P2, so B is now here. And then, now what's left is we wanna move A from P3 to P2, agree? Okay, P3 to P2. So after this, A is gonna be on stack of this. You can now see that, now one more thing to review. Remember the Fibonacci problem we solved before. We say that f Fibonacci n is equal to Fibonacci n minus 1 plus Fibonacci n minus 2. Some of you asked me before, what should be the order of evaluation? Whichever comes first should be evaluated first. So Fibonacci n minus 1 should be evaluated before we ever touch n minus 2. Here, the similar. So now you can see that this part over here is actually some recursive call, this part over here. Before we finish the recursion here, which means we'll get some conclusion like this. Before we get these three moves, we are not going to touch this part because that's actually what follows. Okay? So now you can see that after the orange part, what we get is A and B, they are now on P2. So that's how we achieved from P1 to P2 moving AB. So now when we say move C over there from P1 to P3, now it makes sense because once we get C over here, what's really left is just another subproblem over here that's going to be from AB moving from P2 to P3 and then put it here. Right? Any question about this quick review? But it's really important to see this, how this works conceptually. You will see that the way we do the Java code is very similar, very, very similar. Okay? Any questions? Okay. Now, I want to show you the Java code, and then I will show you that the way we can trace the Java code, I will show you only one part of it, is very similar to how I did over here. Okay? Let's go back to the Java code here. So now we have a tower of Hanoi. Let me just mention one more thing before we see the Java code. The way I'm going to represent the tower over here, you can see the tower over here is A, B, and C. The way I'm going to do this is by using an array. So the way I'm going to do this is to say we have A, B, and C, assuming that the very first position is the top and the very last position is at the bottom. Let's just agree on that. Okay? Now, if you go to the Java code over here, you'll see that we take disks over there, string array. You can think of, in this case, disks at position 0 is A, position 1 is B, position 2 is C. Okay? Now, what we will do is we're going to need some helper over here. Remember what we said before. If you want to make a recursive call on arrays, the way we do it is by using from and to indices. We do the same thing over here. So now what we say is, what we will do is pass the same disks, the reference over there, from 0 until disks length, the length minus 1. This is the same as before. Okay? What's really new over here is, so this 1 and 3 over here means the peg. We want, let me just interpret this for you. This means we want to move the disks from 0 to index 2 in this case, which means I want to move A, B, and C. We want to move them from peg number 1 to peg number 3. So what this really means implicitly is number 2 is going to be used as an intermediate peg. Okay? Now, how do we define this helper method here? I just called it TOH helper, Tower of Hanoi. Let's see, so you can see that it gets a little bit more complicated, but again, this is the reference for the disks of any arbitrary size. And then we have from and to, and also P1 and P2. Okay? So now let's see how we can do it. We say that if the array is simply just empty, that means it's a base case, right? If the Tower of Hanoi of no disks, nothing to do. Okay? I just leave it empty. If from is equal to 2, that means we are dealing with a single element, only single disk to be moved. In that case, it's very easy. You simply say move whatever disk it is from this P1 and then to this P2. Okay? Now, the else part is really interesting. First of all, you can see that the reason that I say 6 minus P1 minus P2, I'll give you one example. If I say I want to move from pack number 1 to pack number 3, what should be the intermediate one? Number 2. 6 minus 3 minus 1, 2. If I want to move from pack number 1 to pack number 2, in that case, what's the intermediate one? 3. 6 minus 1 minus 2, also 3. I'm just making use of the fact that 1 plus 2 plus 3 is 6. Okay, that's why. That's the only trick in this programming. Okay, you might, if you try to Google around the solution for Tower of Hanoi, usually people like to pass P1, P2, and P3 explicitly, but I think that this one might be a little bit easier for you to understand. That's the only trick you need to understand. Okay, so that's why I call it intermediate. Now, let's see over here. Actually, nothing new over here. You're just going to get used to the syntax over here. The same pile of disks. Now, I want to say from and to minus 1. What does this mean? Imagine that if we got an array of A, B, and C, what does it really mean? When I say 0, and remember 2 would be originally 0 up to 2, right? 0, 1, and 2. Now, if I say from 0 to 2 minus 1 would be 0 to 1. That will be only covering A, B. Okay, that's how we specify a subtower. And then I want to say from P1 into the intermediate. And then I can say move the disk from P1 to P2, like how we did before. And then we can say to helper over here, and then I can say from and then 2 minus 1, intermediate, and then to P2. That's the code. I'm going to trace it for you, just to some extent you can understand. But any question very quickly about this Java code here, if there's anything that worried you? Yeah. Intermediate part, yes. So let me just go back to the iPad over here. That will be easier to explain. Let's consider two cases over here, right? So let's say in the original problem over here, when I say I want to move from P1 into P3, right? In this case, you can see the intermediate one would be P2, right? I want to move from P1 into P3. That means I got to stack the intermediate tower into an intermediate pack. In this case, it will be just P2. Now, a clever way to calculate that would be just use 6 minus 1 minus 3. That will be 2, right? That's how I calculate it. Yeah, okay. Okay, so let's go on. Okay, you can also read some description over here. Okay, that's exactly what I said. Now, I want to do a little bit trace with you. You can also see the trace. I'll just refer you to the page if you're looking at the slides. I'll do part of it just so that you understand. Okay, so that I'm going to reproduce this part of it on the iPad. Okay, let's try that on the iPad. Okay, all together. And the way I'm going to do that is very similar to what I did on this page over here. Let's try that together. Okay, let me add a new page over here. Okay, let's see what's our first goal. Okay, now first of all, we know that the problem is we want to move basically A, B, and C from P1 to P3. That's the problem. Okay. How do we specify this problem? As I said before, the way we do it is by saying the array over here is going to be the disk A, B, and C, 0, 1, and 2. Okay, so I'll simply say, to begin with, I would say Tower of Hanoi helper. So basically, I'm tracing this particular method over here. Okay, this recursive method, I'm tracing that. Okay, I just want to show you how close they are between the concept and the code. Tower of Hanoi helper. Okay, let me just do Tower of Hanoi helper. Now, first of all, I'm going to pass, so this is called, let me call it DS, disks. Okay, it's a reference. I pass the reference of the array. Now, the original problem is I want to go from index 0 to index 2. That's the original problem, right? In this case, I would say from 0 to 2. And then I want to move from pack number 1 to pack number 3. Okay, so what you can do is you can think of this way here. I'm specifying this particular array, A and B and then C, right? It's going to be 0, 1, and 2. Okay, any question about this for now? That's the original problem. Okay. Now this problem here is going to be divided into 3 different stages. Let's see the code very quickly. The code says that, first of all, you're going to calculate intermediate. What's the intermediate? Okay, let's just see the intermediate. Intermediate in this case would simply be 6 minus 1 minus 3, which just be 2. So that's the intermediate. Okay? So now, how do we divide this into 3 different phases? Okay? Phase number 1, we should really move the subproblems, right? So now, the subproblem should be just A and B. Just A and B over here. So that's a strictly smaller tower. Okay? That means we're going to make a recursive call. How do we do that? The same method here, to Tower of Hanoi, helper over here. Help me out. What should be the first arguments? First arguments. The same reference, right? DS. Okay? So now, how do I say I want to now have a strictly smaller problem? Used to be from 0 to 2. 0 to 1, very good. 0 to 1. So this really means now we are dealing with only A and B, right? Yeah, just give me one moment. And then you can see that's exactly the A and B we talk about over here. That's a subproblem. Yes, question? The code? Mm-hmm. Yeah, so 6 minus 1 minus 3. You know what, in the iPad over here, just for understanding, I simply just put P1 and P3, whatever it is. In this case, P1 and P3, yeah, let me just, yeah, I'll take a question in just a moment. So here, in this case, P1 is simply 1, P3 is simply just 3. Yeah, maybe that would be, yeah.
I just think it's a little confusing because the parameters for the helper, they're called P1 and P2 instead of like P initial and P final. Because then we actually name the tags P1 and P2.
Yeah. I can improve that, but let's leave with that now. I'll try to improve it, maybe upload a slide. I do see your point. I think the naming over here, just P1 and P3, just pack number 1, pack number 2, pack number 3. Okay? Yeah, yes.
Where in the code are we updating to?
Yes, we'll see that in just a moment. Well, one thing to note, okay? Over here, you can see that the original problem is from and to, and then P1 and P2, right? So what we really did was, once we figure out the intermediate, we make a recursive call. So we still have from, but it's now 2 minus 1, right? And then we have P1 to intermediate, right? That's where we actually change it, okay? Okay, now let's go back and then, okay? So now we know what the intermediate is. So now we want to say, we want to move A and B, the subproblem here, from where to where? It should be from, the ultimate goal is from P1 to P3. That means intermediate goal should be from P1 to P2, right? So now in this case, I'll just put P1 over here and then P2 over here. And this P2 indeed is the intermediates. Okay, this is just P2 for now. Okay, what about the second one? Second stage. Second stage would be, we want to move the bottom one, right? The bottom one should be simply just 2 over here. Right? So the bottom one would be, we can say move, over here, we can say move ds at position, simply just 2, over here, okay? From P1 to P3, over here, right? Now, third stage, let's try to test if you can understand to some extent. Now, what should we do over here? First, arguments. Yes, okay, that shouldn't be too surprising. Now, what should be the front and to in this case? You can see the first recursive call over there is 0 and 1, right? That means we are moving the subtower. In this case, we are also moving the same subtower from the intermediate one back to the destination, right? So now in this case, we also get 0 and 1. That also means AB. Okay, so now over here, what should we do? 2 more parameters to specify, 2 more. So now the subtower is now in the intermediate pack. We want to move that from the intermediate to the destination. Yeah, P2 to somewhere, right? Okay. It should be P2, right? Because P2 is the intermediate, right? So we should put intermediate here. And in this case, because destination is P3, so we go to P3. So far so good? Okay, now, one more thing to point out. I just want to point it out very quickly. Now, what about this part here? You can see that this part here is also a recursive call. Now, how can we figure that out? Let's do that very quickly, okay? For this one here, it's actually organized a little bit better on your slides, but I just want to make some point over here. Again, for this one here, we also get 3 stages, right? For each recursive call for the Tower of Hanoi, you got 3 stages. Now, for this particular one, let's try. To Tower of Hanoi, helper. First parameter always ds over here. Now, you can see that the problem we are solving is just A and B, right? From 0 to 1. How do we make a sub-problem out of it? From where to where? 0 to 0? Okay, good. 0 to 0. You can see that we always increment, we just decrement the 2, right? You can see that, just want to point out to you. You can see we always say 2 minus 1 over here. That's a trick, okay? Now, okay, 0 and 0, and then now, one more. So what should we do over here? Now, what's the problem? The problem is it should be from P1 to P2 for this problem here. That means what's the intermediate in this context? P3, yep. I'll just say intermediate is P3. 6 minus 1 minus 2, P3. So now we should go from where to where? P1 to P3, exactly. P1 to P3, that's the intermediate. And then we can say move, and then here we can say disks over here. Okay, we can simply say 0 over here from P1 to P2, right? Destination, okay? P2. And then, again, one more call over here. Now, disks over here, the same sub-problem there. So from 0 to 0 over here. Now, what should we do? From intermediate back to the destination. Intermediate is P3. And destination is P2. It's a very quick trace for you, but I would suggest to really get the most out of this, review what's really conceptually required for this problem here, go over the code by yourself. If you really got trouble, come to me, okay? If you really want me to trace to every detail, it might take 2 hours. Well, I'm exaggerating, not 2 hours, but just that's not the only thing we want to teach in this course, but hopefully you get an idea. Any questions about this before I move on? Okay, now, you can also play with the source code. And now one more topic about recursion before I move on to a new topic, which is about trees. Okay, one of your course learning outcomes is you want to informally prove that your recursive method is correct, informally. Okay? Informally means as long as you follow a certain pattern that makes sense to me, you'll be okay. We don't have to do mathematically formal. Okay? Now, this is kind of one simple problem I'll give to you. I'll show you how you can go over that. It's very straightforward. And then you should really try the same pattern for every recursive method that we have gone through. Okay? The actual exam or the test would be no more difficult than that. Okay? That's what I can say. Okay, let's try this one here. Let's say we are trying to figure out if the array A over here, integer, are all positive, right? And then the way we do it is just a verbatim copy from the previous slides. We call the all positive helper over here from 0 until a.length minus 1. Okay? And then you can see that line number 1, the method itself is not recursive, right? But starting from line number 2, we are defining a recursive helper method. And then we have the same array A, the reference from and to. Okay? Again, we got base case. If from is larger than 2, that means the array is empty. In that case, we cannot find any counter example like a negative number. So that means we should return true. Okay? Else if there's a single element in the array, in that case, depending on whether that single element is positive or not. Otherwise, we're going to make a recursive call. And the way we make a recursive call is we're going to say all positive helper from plus 1. Okay? So that means we shorten the range of search by 1. Okay? And then we combine the result from our friend, the recursive call, with whether the current element from is actually larger than 0 or not. Combine the result using conjunction. So that's what we learned from before. The way you prove is by mathematical induction. Very easy. I tell you what you should do in general. Basically, the way you prove by mathematical induction is you do base cases and also do recursive cases. And for recursive cases, you're going to assume some inductive hypothesis. What you assume is the recursive call over there in line number 5 is going to give you the correct result in a shorter range over there. That's what you can assume. And then you combine whatever that's returned together with the expression over there. You argue that it's correct. Okay? So we first of all prove that all positive helper is correct. And then we say that because itself is correct, when you make a call to it in line number 1, you say all positive helper from 0 to eta length minus 1 is going to cover the entire array. So the all positive method is also correct. That's kind of the roadmap for the proof. Okay? I'm going to show you the complete details. Let's see. Let's go over. What I just said was just a roadmap. Okay? Let's see. We're going to prove by mathematical induction. We use mathematical induction to prove that the recursive helper method here is correct. Okay? Only the recursive method. Now, how do we do that? Two cases. First of all, base cases. So there are two basic base cases we should really handle for array. Empty array and array of only one elements. Okay, let's do that one by one. In the case where empty array, first of all, we got to argue what should be the expected result. It's a little bit like writing JUnit test, right? You're trying to actually say what the expected result is and then test your program to see if the actual result is really what you expect. So now we expect that in the case of the empty array, because we know that there's no counterexample to prove that it's not all positive. So in that case, that should return true. Now, question for you. Which line in your code handles this case? Line number 3, right? So first of all, state what's really required and tell me which line of the program does that. In this case, line number 3. So base case number 1, done. Okay, you can see the pattern, right? Okay, base case number 2. In the case of array of size 1, we know that the result should depend on what that element is. If that element is positive, result should be true. If the element is not positive, result should be false. Which line handles this? 4, exactly. You got it. Okay, so we just proved the two base cases. Okay, of course, only for this example, you really got to practice. Okay, inductive cases. This one is slightly more sophisticated, but it's not too bad. There are two stages for this. First of all, let's make some inductive hypothesis. Okay, inductive hypothesis in this programming context means when I'm trying to make a recursive call, here I'm just making one in line number 5. I'm assuming that for every recursive call I'm making, it's going to return back to me the correct result. I can assume, okay, on a smaller problem. Okay, so let me just give you one example here. Over here, I say that if I'm trying to make this recursive call, A and also from plus 1 and then 2, basically starting from the second from the from plus 1 index until the end. Okay, I say this one returns true if all these elements, so from plus 1, from plus 2 until from A and then 2, right? They're all positive. Otherwise, it's false. Can you just read through the inductive hypothesis for me, and then see if there's any problem here, any question, before I move on? So this is the most critical step, right? So here, since we said informal, so we just had to write it out, okay? If we want to do it formally, we had to use some maybe for all universal quantification, like what you learned in 1019, but that's not the course learning outcome. Let's do it informally. Okay, so this is what we're going to use. Again, when you try to make inductive hypotheses, you only make them not really on the original problem. That's something you want to prove. You only make the hypothesis on a smaller problem, the recursive call. Okay? Okay, so now, let's see how we can continue. And the way we're going to continue is, let's say I'm trying to handle an array of size eta length. Okay, that's the size. From 0 until eta length minus 1. Now, how can I handle that problem there? Basically, the intuition is, now I can split this problem here into two parts, A0 and then A1 until eta length minus 1, right? So these are the two parts. And then to see how we can continue. Let me just read it out, okay? So now we know that this is the original problem. We have the array A and also from and to, okay? This should return true if, first of all, A at position from is positive. right? The first element. That's the first part of the split. What about second part of the split? That would be A from +1, from +2 until A2 are all positive, first and 2. Okay. These two parts. Part number 1 over there can be easily done just using A at position from is larger than 0. What about part number 2? Yeah, it's a recursive call, and we already assume it's going to give us a result, right? You can see that one there, A from +1 from +2 until 2 is exactly what we assume about in the inductive hypothesis. Okay, so now we can say that what we have is, so now by inductive hypothesis, we know that we can simply say the first element, if that's positive or not, and whatever we return from the recursive call. Right? So here I'm just using conjunction, just to be a little bit fancy. Okay. Now, what do we do later? Okay, oh, I just showed that. Basically, this one is handled in line number 5, right? That's exactly what's handled in line number 5. Okay, so up to now, what we have proved was the all positive helper method is actually correct. That's what we have proved. Okay, but how do we prove that all positive, this method over here, is correct? We should say that since we know that this all positive helper is actually correct, and we are also specifying the range that covers the entire array, so that means this method must be correct as well. Okay, that's kind of the reasoning. Okay, so we can say that this method here is correct because we're passing the right indices range, so they cover the entire array. And this is covered in line number 1 over here, of course. Any question about this proof over here? I'll give you some more examples to practice, but this is really the general pattern you're going to follow. Proof by mathematical induction. Are we okay? Maybe you should go over the slide and then to see if you're okay. Okay? There will be definitely some question about this, about how you can prove if some recursive method will be correct. But I'll try to be nice to you. It should be no surprise to you. As long as you follow the pattern, you understand all the methods we covered so far, you should be okay. Okay? If really no questions, I would like to move on to binary trees. Okay? Okay, let me talk about binary trees. Okay, I'll see how much I can go. Okay, let's talk about what's the concept for trees. Okay, so far we talk about linear data structure, like for array and also for linked list. I briefly talk about what's the difference between linear and nonlinear. Linear means you have the concept of before and after. In the case of the array, what's the element before index 3, index 2? What's after that, index 4, right? Now, in the case of the singly linked list, you also got the notion about what's the next node for this current node. You just go use the next reference, right? Okay, that's kind of the linear structure. Now, we're going to show you something that's also so doubly linked list, you will learn about it in 2011. I just mentioned the name over here. You don't have to worry about doubly linked list for this course. Well, we're going to talk about something called tree. And for tree over here, it's nonlinear because the notion you have is no longer just before or after. You've got the notion about more like a hierarchical concept, above or below. Okay, we'll see example in just a moment. Okay? Okay, and now, before we do any meaningful operations on the tree, we want to introduce some terminology. This one here, don't panic too much because whatever terminology I'm going to introduce, they correspond very closely to family trees that you maybe learned from social science or from your high school. We'll see what it really means for parents, siblings, children, ancestors, and descendants. Okay, so these are all familiar terms. Okay, but we'll see what it means in the context of computer science, data structure. Now, let's say this is the family tree we have. Hopefully you can read it. I'll read it very quickly. David here at the top, Ernesto, Chris, Elsa, Anna, Shirley, Vanessa, and Peter. Okay? Now, let's introduce the concept very quickly. First of all, root of the tree. If you think about in reality, of course, for the tree, the root should be at the bottom. In data structure, it's exactly on the top. Okay? That means David is the root. That's number one thing to remember. Okay? Okay, so now root will be David. Now, what about parents? Given any node, how can we figure out the parents? This is how you can think of it. For example, if I got Chris over here, if I want to figure out his parents, I just need to go above one level. Okay? In this case, David. You have only one parent in the tree, right? Not two parents. Yeah. Now, what's the parent for Vanessa? Elsa, good. Okay, quick check. Well, right? It's easy, right? Now, children, the opposite. So now children means all the nodes immediately after you, immediately below. For example, what's the children for David? Ernesto and Chris. Notice that you wouldn't say, well, in this case, we wouldn't say Elsa is a child of David. We don't say that. It's a grandchild in some way, right? But we would say Elsa is a descendant of David. Okay? Just notice that David has only two children, Ernesto and Chris. Okay, that's also easy. Okay, what about Ernesto? No children, and there's a special name for this. Okay, so now one way to say that is let's compare David and Ernesto. David has at least one child. In this case, we say David is called internal to the family. However, Ernesto has no children, in some way contributing nothing to the family, and he's external. Well, it's very, old-fashioned way of, huh?
What's the name?
Ernesto, external. You'll see that in the next slide. Okay, that's how they derive the name, of course. Yeah. Okay, now let's see that. Okay, ancestor. Now here's very important because when we talk about inheritance, you're also gonna use the notion of ancestor. Now, what does it really mean for ancestor? Ancestor means your parents, your parents' parents, your parents' parents' parents, all the way up to the root. Also, plus yourself. You are also an ancestor of yourself. Okay? So now, for example, who are the ancestor of Vanessa? Elsa, Chris, David, and Vanessa, right? Don't forget herself. Don't forget, okay? It's kind of very easy to get missed. Who are the ancestor for David? David, exactly. Very good, you got it. Okay, now let's talk about descendants. Descendants, basically yourself, plus your children, plus your children's children, plus your children's children's children, until the very bottom of the tree. Now, let me ask you in this way. Who are let's say, talk about all the nodes in this tree. Who has got the least number of descendants? Shirley, Vanessa, Peter, and Ernesto, because they have only themselves as their descendant. Oh, so what does that mean? You are the ancestor and descendant of yourself. Okay, just according to this terminology. Now, which node on the tree has the most number of descendants? David, the root, always the case. Okay? Yeah, the terminology is easy. Okay, sibling. Sibling is easy. Means if you have the same parents, sibling. By the way, we don't have anything called relative for the tree. Nothing like that. Okay, only sibling, fortunately. Okay, now here comes the most important part. Let's talk about subtrees. Subtree means, so now, let me give you a little bit preview. We're gonna talk about how you can do recursion on trees a little bit later. So the way you do on recursion is on recursing on the subtrees. Okay, let's talk about what subtrees are. Okay, let me just move to the iPad and give you some idea. Okay, that's a tree. First of all, let's see over here. Let's talk about David over here. David is the root, for example, in this case. So now I can say David has two subtrees. Okay, the first subtree looks like this. This is the first subtree. And the second subtree is bigger. This is second subtree. So what's the root for the first subtree? Ernesto, right? Yeah, so this is the root for the first subtree of David. And apparently you can see Chris over here is the root of the second subtree of David. Okay, let's just do, in the subtree, the concept is really recursive. Let's say now, let's now focus on maybe quiz over here. Now, how many subtrees does quiz have? 2. This is the first subtree. This is, oh, sorry about that. Yeah, thank you. Sorry, saw that the wrong way. This is the first subtree over here. This is the second subtree of quiz. Okay? Are we okay? Okay, let me add a new diagram and ask you one question. Okay, just let me go by the slide and then I'll add a diagram. Okay, subtree, and then we talk about external and also internal, right? External nodes, or you can call them leaves of the tree, which means they're basically at the bottom of the tree and they simply have no children. Okay? Internal nodes means they have at least one child, at least. Okay, so these are just terminology you can get used to. Now we got exercise here for you. Let's say over here, how many subtrees are there in this tree? How many subtrees? I heard 14. Any other? 16? 14 and 16? What about we take the average? 15. Why 15?
Is the whole tree a subtree of itself then?
Yeah. Okay, let me first of all let me ask you this question here. What is the largest subtree in this case here? Just A, right? Just whole itself. Oh, let me correct you a little bit. When I say what's the largest subtree, when you say A, it's not quite correct. You should say the subtree that's rooted at A. Okay, that's really important to say. Okay, let me just basically it's a very easy question if I put this on the exam. How many subtrees? Just count the number of nodes, because each node can be the root of some subtree. Okay, I'm giving you more. So 15. Why? Let's think about the size of the subtree. Now, what's the minimum size of the subtrees? Minimum. 1. How many subtrees are there of size 1? 8. 8 sounds good. Which 8? HIJKLMMO. Right? H is itself a subtree, right, of size 1. I is also itself a subtree of size 1. Okay, getting better? Also leaf, yeah, it's different terminology here. So, okay, now, do you have any subtree of size 2? Really? What's the size of D? The subtree rooted at D? 3, right? It should be D, E, and I, right? It's not really just, sorry, it should be D, H, and I, not just H and I, right? So there's no subtree of size 2, okay? So now, how many subtree do we have of size 3 then? How many? 4. D, E, F, and G, right? Okay? What should be the next level? How many? 7, right? Very good. Okay, you seem to get it. 7. In this case, for example, B, the subtree rooted at B, so you got 7. Subtree rooted at C, also you got 7, B and C. Okay, finally, you got also the biggest subtree of 15. In that case, you got just A. Don't worry, I wouldn't be so mean. I'll think about it. I might give you a tree, for example, where I will ask you to draw me the second largest subtree, or second smallest subtree, something like that. Okay. Don't worry I'll worry about that. Don't worry. You don't have to worry now. Yeah, it's too early to worry about this. Okay, guys, any question about what we talked about so far? It's very easy, right? It's nothing challenging. Huh? How is it controlled in code? I will see some code in a bit, okay? Okay, let's see, go on. Okay, let me just something very important about tree. So this sounds something you should really know. If I draw you something that actually is not a tree, so you should really know how to judge that, okay? So this is something very principle for being a tree. So there should be a single unique path from the root to any particular node. I'll show you what. For example, using here, so these are trees. For example, this is the root over here. For this root to go to any node in the tree, it's only a single path. Let me show you something that's not a tree. In this case, so you can see that, for example, to get to this node, how many paths are there to go from the root? 2, right? You can either go this way or you can go this way, like a diamond shape. Okay? It's very easy to see. Good. By the way, in this case here, it's called a graph, not a tree. So that's the most general data structure you may have. So you will learn that about the end of 2011. Okay, you'll learn that, not in this course. Okay, we also got notions about the trees being ordered or unordered. The concept is very easy. So now in this case, what does it really mean for the tree to be ordered? Order simply means you usually talk about first child, second child, third child, fourth child. So the sequence of the children actually matters. So when we talk about binary tree, it's actually a kind of order tree because we talk about left and the right. Okay, we'll get there. One example here, let's say that's the tree structure for your book in this case, right? So that means the preface should go before part A should go before part B should go before references, right? So the sequence of the children actually makes sense, matters. Okay, that's one example for order tree. What about unordered trees? That means the order of the children does not matter. One case could be, let's say that's your home directory structure. In some way, the way you order, the way the directories or the files are ordered doesn't really matter, right? Okay, just one example. It's a design choice, exactly. So Raymond just made a very good point. Whether your tree should be ordered or unordered is a design choice. Depends on what you need for your application. Yes, go ahead. Yes. Leaves or external nodes. Yeah. Mm-hmm. They don't. Very good question. The question was, let's take market, for example, over here. So we say that market is a leaf or is an external node. And there's, the subtree that's rooted at market is just itself. Okay, yeah, okay. Okay, let's go on. Binary trees. So up to now, we talk about general trees, which means the number of children for the tree can be unlimited. But now we talk about a special kind of tree called binary tree. Okay, the definition is simple. It's an ordered tree, which means the order of the children matters. Okay, so these are the properties of binary tree. Each node has at most 2 children. It can be 0 child, in which case it is an external node. It can be 1 child, or it can be 2 children. Okay, 0, 1, or 2. And then now we say that when you have children, you say the left child and right child. Okay, left and right. Okay, since we got only 2, that's why it's called binary. And also left child goes before the right child. Okay, yeah, because the sequence matters. Okay, let's see some terminology over here. So now for each internal node, which means the node has at least 1 child, right? Okay, now. Okay, we talk about left subtree and right subtree. Okay, let me just show you one diagram here so you will see. Let's see this binary tree over here. So now let's see this. For example, you can see that for this tree here, you can see the left subtree. Well, I used to say first, second, and third. So now we guarantee you got at most 2 children. So now we can say that A has 2 children, B and C. So that means A has 2 subtrees, left subtree and right subtree. In this case, what's the root for the left subtree? B. And the root for the right subtree, C. Similarly, how many subtrees does B have? 2, right? Left subtree rooted at D. Right subtree rooted at E. Okay, that's easy. So left and right. Now, one more thing to mention. So we are going to see some, what about for H? H, conceptually, you can also think of, H also has 2 subtrees, left and right, but just that they're both empty. Okay, just conceptually. Okay, so now you can see that A's left subtree is rooted at B, and the right subtree is rooted at C. Now in this case, for H, for example, H is external. In that case, has no subtree, or you can think of both subtrees are empty. Okay, just a different way of thinking. Okay, now, recursive definition. Okay, let's try to get a little bit more used to defining trees in a recursive way. Okay? Now, let's see this. A binary tree, now, is either, what about base case? just empty tree, just nothing there. Or it's actually some non-empty tree with a root, okay? And the root itself has left tree and right subtree, okay? Let me draw one example right away, okay? Okay, let's see, and then I'll talk about recursion very quickly. Now, let's say, let me just do another one over here. Okay. Let me just image photos. Let me try to do this one here. This one might be too complicated. Give me one moment. Let me, how can I just undo? Okay, good. Let me just do another one. That one's too complicated. What about just this one here? Okay, that one's good. Okay, let me give you an idea over here. Now, how do we define a tree? First of all, you can think of it as, first of all, A is the root. This part over here is the left subtree of A. This is over here the right subtree of A. So far so good, right? That's a recursive definition. Now, you can think of it as, let's now shift our focus to B. Now, in this case, we can say that the left subtree of B is this. The right subtree of B is over here. Okay? Let's now shift the focus again to another node. Let's say D over here. So now, the left subtree of D is simply just H. The right subtree of D is just I itself. And then let's go even further. What about, let's talk about J over here. What about J? What's the left and right subtrees? Empty. Very good. Okay? You can see that we can always talk about the subtree depending on which root you're talking about. Okay? So now, let me give you, I'll get back to recursion in just a moment. Okay? Let's go over some slides. Okay, now, how do we solve problems recursively on a binary tree rooted at R? Okay, I will just go over a slide and then I will tell you what that means visually. If you want to do something like that, in the case of the array, you do something with the first elements and do something with the rest of the array, the subarray. Similar here. You do something with the root and then recursively solve the problem on the left subtree, recursively solve the problem on the right subtree, and combine the solution together. Okay, that's kind of the idea. Okay, recur on left subtree and recur on right subtree. How do I know if the problem I'm solving on the subtree is strictly smaller? How do I know? Why? Think about that. So now, let's talk about A over here. How many nodes are there for the subtree rooted at A? 10. Okay, I just counted 10. Okay? Okay, we got 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10. Okay, good. So now, how many nodes are there for the left subtree for A? Well, it's at least it's guaranteed to be smaller, right? It's some number that's guaranteed to be solved because you at least take out A itself. It's guaranteed. That's why so now we are really recurring on a smaller problem. Okay? So now, let me give you some idea just about how you can calculate the size of the tree. Okay? Let me just do another page over here recursively. We do have some recursive method that's called size, but I'll get to that code in just a moment. Let's see the diagram. Okay, I want this diagram to be here. So now, how do I calculate the size of the tree? Okay, let's think about how we can do that. Okay, now the size of the subtree rooted at A. We know that the answer should be 10, but how do we get that, right? So now we know that the node itself should be counted as just 1, right? And now, how do we solve the problem recursively? If you just keep going to the left, you're not really solving the problem in a general sense because you simply don't know how far you should go. And once you get to the furthest end, how you can? Okay, that sounds a little bit more recursive. So what Ken just said was, so now let's worry about, first of all, this is the left subtree over here for A. And this is the right subtree of A. Okay, you simply just ask about what's the size for this left subtree. And also what's the size for this right subtree. Let's just try to see this particular subtree on the left. What's the size for this particular subtree rooted at B? Also, we don't know immediately, right? We haven't really reached the base case yet. The base case should be just a single node, an external node. In this case, we can, let me use a different color here. So now we are talking about B over here. In that case, we can try to recur again. Left subtree over here, and right subtree over here. And then we can simply ask, what's the size over here? And what's the size over here, right? Now, let's again shift the focus. Let's now go to D over here. Again, it's too big for us to solve, okay? Left subtree over here, and the right subtree over here, okay? So now, we can see that H is external nodes. In that case, the size should just be 1, and I should be 1 as well. 1 plus D itself, we get 3. So for the pink subtree over here, the size is 3. Any question until now? For H and I, yeah. So here, graphically, it's easy to see. But programmatically, whenever you see that the node has no left child and no right child, both are null, that means you're reaching the base case. Okay? So now for the pink subtree over here, we got size 3. Similarly, how do we figure out the size for this subtree over here? Again, this is too hard to solve right away, right? So we figure out what's the size for the left subtree here, and what's the size for the right subtree over here. What's the size for the left subtree in this case? 1. What about right subtree? 0 conceptually, because it's just empty, nothing there, right? So that'll be 1 plus 0 plus the node itself. So we got 2, okay? So the size should be 2. So that means the left subtree for B has the size 3. The right subtree for B has the size 2. So 3 plus 2 plus the B itself, we got 6. So that means the left subtree of A has 6 nodes over there. Okay? Guys, any questions just to see the illustration? So basically the way I'm doing this is every time you want to solve a problem for the entire tree, if the tree is too big for you to solve, basically you just break down the problem into 2 parts. Left part for the subtree, and right part also for the subtree, the 2 different subtrees. And then combine the solution there and then do some combination. Okay, that's exactly what I do. Any questions? Yes? Without recursion, I can say no. Yeah. No. You can try. Well, I would say no. Hey guys, any question? Yes? Yeah, so okay, let me give you a little bit idea about implementing this, but we'll see the Java code in just a moment. Imagine that in the case of the singly linked node, we say that there's only one reference to the next, right? So now imagine that for every node in the tree, we maintain 2 references, left and the right. How do we know if the node is external? Well, if left and right are both null, that's external. That means you're reaching the base case. If either one of them is not null, that means it's internal. Okay, good. Hopefully that's clear. Go ahead.
Is this similar to how you find an element inside a tree?
Let me save that. Yes. So, okay, very good. The question was, let's say, okay, since you already talked about that, how about we do that very quickly? Okay, let's talk about this pace over here. Okay, let me just put the same diagram over here. Okay, this one here. Okay, good. So now the same tree. Now let's try to practice a little bit differently. Okay, so now let's say I want to know if the tree has H. True or false? Well, should be true in this case, right? Now, how do I figure that out recursively? Similar idea. Yes? Just stretching. Okay, no worries. Wow, that's good. I like that. But you want to speak out for this one? Yeah, okay, good. All right, let's say if we have H in this tree over here. First of all, we know that this problem here is way too big for me to solve to starting from here. But I can at least compare if A is equal to H. No, right? So now, do I have a chance? I have a chance because the H might be here in the left subtree, or H might be here in the right subtree. Either way. Is it here or it's here, either true or false? So I can recurse to say has over here, I can say A dot left. And then has over here, and then A dot right. I'm recurring on that. And then when I am recurring on this particular node, this subtree over here, starting with B, also it's too big for me to solve right away. But at least I can compare if B is equal to H. No. But do I have a chance? I still have a chance because H can either be here or it can be here. Okay, so now when I'm trying to solve this particular subtree here, D also too big for me to solve. D is not equal to H. I still have a chance. This is the left subtree of D. This is the right subtree of I. Now, H is exactly equal to H. So now I can just return true from here. Right? So now think in this way. So now has of some subtree rooted at A would be equal to, I mean just put it a little bit mathematical, defined as either A is equal to H or has A dot left or has A dot right. So you will see exactly that kind of recursive call in the Java code. Okay? So you can see that when we are trying to make the recursive call, why can we claim the problem we are trying to solve is strictly smaller? Because we are recurring on the subtree, which is guaranteed to have a strictly smaller size. Okay? Questions? Yes.
If we were looking for G,
Uh-huh.
go through the whole tree first and then go to the right?
Exactly. So now you can see that, well, since we don't, so the way what I decide for this section here is I don't really talk about the concept called binary search tree because I want to save the most of the time for inheritance. So what we'll do is we only do the binary tree. But I'll give you a little bit preview. Okay? You can see in this case, we simply don't know if, let's say H. When we say H is not equal to A, we don't know whether H will be on the left-hand side or right-hand side. So we're going to check both sides. But when you learn about binary search tree, there will be a special property for the binary search tree such that when you know that the key is not the same, you will know where to go, either to the left or the right, like what the binary search you did last time. But let's not worry about that. Okay? For this section here, you only have to worry about binary tree. You'll learn about binary search tree, so I don't want to repeat what they would say in 2011. Okay, any questions for this? Yes?
How can you use recursion or general?
Good question. The question was, how can you use recursion on a general tree? I'll give you some idea. Okay? So you can see in this case over here, every node has left and right references, right? In a general tree, you have an array of references, right? In that case, what you will do is you're going to run a loop to say for integer I equal to 0, I less than children, let's say the attribute children.length, and I++. Inside the loop, you simply recur on that. Okay? But don't worry about that. Okay, good. Now, I would like to continue over here. Okay, you can see that. So that's how we recur. Application for binary tree, okay? So I'm just going to show you two applications over here. The first one is something called decision tree over here. Decision tree simply means you can say each internal node has basically just has some description over there, and then you can have either yes or no. If yes, you go somewhere. No, you get somewhere. I'll just give you one example. Let's say I'll read it out. That's the decision tree for passing this course, for example. On the top, do you attend classes regularly? Either yes or no. For those of you who are here, yes. Right? If you say yes, so I would say you may pass with 30% confidence, 30%. If no, I would say, if you didn't do that, do you try out all the code examples? If no, I would say, do you ask for help whenever you get stuck? If still no, what I would say is, you may pass if there was a miracle. Yeah, something like that, right? But you kind of see the point. The example here is not really important. I just want to show you that that's one possible application for binary trees. Okay? That one is not so much interesting. What's really interesting computationally is the second application. We can represent what you are familiar with, for example, arithmetic expression using a tree. For example, let's say we got some expression like that, right? We're using multiply, divide, plus, and also minus, right? The ordinary or arithmetic operations. Now, how do we express this as a tree? Okay? This is how the tree looks like. But we'll get to the tree in a bit. Okay? I just want to show you that there's one possible application. Okay? And now, let's say we're given this tree over here, but now, how do we, for example, print out the expression from the tree into the string representation on the top? How do we do that? And also, how do we evaluate this tree over here? So what you got to do is, you got to learn about how to do traversal of the tree, which means we're going to systematically traverse the tree one by one into the node in a way so we can accumulate the result or to visit the node one by one. Okay? We're going to learn. So there are 3 traversal methods you have to learn. I'm going to go over that. Once you get one of them, the other 2 are very easy. Okay, tree traversal algorithms. So there are 3. The first one, okay, let's go over what tree traversal really means. That means we're going to systematically visit all the nodes in the tree, all the nodes. You cannot miss any one of them. Okay. Now, and you might want to do for different purposes. For example, you may want to print out everything on the tree, or you may want to evaluate, or you want to determine if every node, if you store integers, every node has the number larger than 0, for example, right? You did some analysis you want to do on the tree. Okay. Now let's learn. So there are 3 different types for the tree traversal you got to learn. Okay. Let me just go through the first one. So the first one is called in order traversal. This is the idea. You're going to recursively visit the left subtree and then visit the root or the parents of the current subtree, and then recursively visit the right subtree. Okay? I'll give you a little bit pseudocode, and then we'll do example. If I say in order on a subtree rooted at R, if R is not equal to null, that means I'm dealing with something that's not empty, right? In that case, I can say recursively call in order and then go to R's left child. And then I can say visit this current root, R, and then recursively do in order traversal on R's right child. It's only pseudocode. Okay, yes? You're gonna visit the parent itself, which is R in this case, right? It's R over here. Okay, let's now get an idea. Okay, let's now see some example over here. Okay, now for this tree over here, what does it really mean when I want to do in order of A? What does it really mean? Okay, let's try this. When I say in order of A, by definition, this is what I would do. Okay, I would first of all, I would need to say in order A dot left, go to left subtree. And then I will annotate the graph in just a moment. And then I will just print out A. And then I will do in order, and then I'll say A dot right. Okay, so that means basically I'm going to do the following. So I'm going to do the in order traversal of B over here, and then I'm going to do A, and then I'm going to do in order traversal of this, of that. Okay? Now, what's going to be the in order for this? What's A dot left? B. Okay? What's going to be the in order for B? Well, it's going to be, well, be careful, because B is over here, so we're going to say in order recursively on B dot left. Okay, and then what? B. Thank you. In order B dot right. Okay, you kind of get the idea. Let's just trace this very carefully, but you will see that it's actually not that difficult if I do it a little bit more quickly. Okay, so now over here, what about, so over here, so this is in order, over here, in order B dot left. So this is B dot left. Now, how do we do this particular in order? So this is D, right? Okay, so now in order, I'll say IO. In order, D dot left, H. In order on H, and then D, and then in order of I. Agree? Now you can see that now we have reaching some base cases. In order of H, basically we are reaching some external nodes. They have no left child, no right child, base case. So now that means we can simply just print out H. So H is the very first thing we print out, H. Okay, so I'll put H here. And then D, next one. And then I. HDI. In order of H, just H itself. Thinking this way. Yeah. So in order of H, let me just write it out, maybe aside. In order of H is going to be like this. It's going to be in order of H dot left. In this case, just empty. Right? I'll say empty here. And also, you're going to be H, and also in order of H dot right, which will also be empty, right? So that's just H itself. That's why. Okay, so now we got HDI, and then HDI, and now what will be the next? So now that means HDI correspond to the in order traversal for D. Which means if you try to do the in order traversal on D, what you will get is HDI. Okay, what's the next? B, right? Because now B is left here. It was suspended, right? So now B. And then what would be the in order traversal for B dot right? Okay, yeah, it should be in order on E, right? Yeah. So now tell me the result. What's going to be in order on B dot right? JE or EJ? JE. Well, I heard somebody said EJ. Okay. Think about this. The reason that it should be JE is because if I want to do in order traversal on the subtree rooted at E, I'll do the left subtree first, which will be J, and then E. So that'll be J and E. So, and then I got J and E over here. So this is the in order of the subtree rooted at E. Okay, guys, follow so far? Okay, let me change a new diagram. It's a bit too messy. Let me just try to present in a slightly fast motion way. Over here, what I would do is, oh, actually not here. Okay, I want to insert a new page over here, add a page below, and image, photos. Okay, I want to do this one here. Okay, let's try it one more time. Okay, now let's say I want to do in order on A. Let me first write out the result. H, D, I, B, J, E, A, F, C, G. Okay, for those of you who don't get it, I'll try to analyze the result to you. Okay, let's try. First of all, I can see that the green part over here, HDI, this is the result for in order on D, right? HDI, that's the simplest case. And then you can see that J and E over here is actually the result from in order of E, right? Because left, parents, and no right. So now you can see that I can also combine these together over here. If I combine the in order of D, combine with B, and also in order of E, I'm basically getting the in order of this, right? Right? So this is the in order traversal of B. And then you shouldn't be too surprised if I say this part over here is the in order of what? C. C, right? Okay, yeah, C. Good. And then if I combine the green part, the red part, and also A together, that will be the in order of A. Are we okay? Guys, how about do one practice, okay? I kind of wanted to leave this exercise for you, but when you actually see the slide, that tells you exactly what I said. I will leave that to you. Let's do one exercise. Oh, don't worry about pre-order, post-order. Now, look at this tree over here. Tell me what the in-order traversal is. Let me do, I'm not sure how well this might work out. Let's do something like this. Start from somebody, tell me the first one, and then I'll point to another person, tell me the next one. How about that, in-order traversal? I'm not sure how this might. Start first. In-order traversal. Plus? Okay, no, wrong. Don't worry. Who want to be the first one? Yes. Are you stretching or you want to say? Okay, first one, in-order traversal. Yeah, let's say in-order traversal starting from minus the top. What's going to be the first one being printed out? Okay, who want to be the first one? That's too much. That's too much. The first one, tell me the first one. Yeah, 3. Okay, second one, 3. And just raise your hand. 3 plus 1. Okay, just say it together. 3 plus 1. Multiply 3. Divide 9 minus 5 plus 2 minus 3. Multiply 7 minus 4 plus 6. Wow, amazing, amazing. Is it because you are too smart or I teach too well? Okay, how about we got another 2 or 3 minutes? How about we do something very quickly, okay? Just to get something done. Okay, guys, I want to just say something here. So you pretty much know the in order. I want to finish pre-order, post-order very quickly, just 3 minutes, okay? Because the way we do pre-order, post-order is you just swap the way you do the recursion. Now for the pre-order here, that means you can see we visit the root first, and then the left child and then the right child. Okay, that's the pre-order. Root first. Post-order, you do the left child first, right child, and then the parents. Okay, why don't we try? How about this? Let's try the example there. If we didn't get it right, you cannot go home.
What if one person gets it?
Why don't we try? How about this? Let's just try the simple tree, okay? Okay, let's try pre-order. Here's the principle. Pre-order means the parent first, the left child and the right child. First one, pre-order. A, B, D, H, I, E, J, C, F, G. Amazing, amazing. Okay, post-order. The principle for post-order is left child, right child, and then parents. Let me try. When you want to start as much as possible, give it a try. Left and then right. H, and then H I. You just do as much as possible.
H I D. J E B F G C A.
Wow, exactly. Wow, guys, amazing. Okay, give me 30 more seconds and then we're done. Okay. Now, so this is the principle for in order, pre-order, post-order. I'll leave the simple example to you. Okay, very easy to go over. And then the exercises. Okay, I will start from implementing the binary tree next time for just 10 minutes. Okay, because I really want to move on to inheritance. But that's all you need to know for binary trees. Okay, see you on Thursday.